Welcome to the review. Today, xanderheads, I have some magnificent questions for you in differential equations, and this is going to be the capstone of that series for now. It's going to be the middle, and there will be more videos after that, but this will do. So, ordinary differential equations, we've checked separable differential equations, we've checked homogeneous, linear, exact, and even Bernoulli and special linear stuff. So we're going to tackle all of that in this one video with 10 examples. So first, let's review this question. X squared y squared plus 2xy squared dx equals, no, plus quantity x plus 2 dy equals 0. Is this separable? Is this what? How do we figure out if it's separable and the others? I usually like to refer to this branch. So separable, separable. There we go. So is it separable? If it's yes, then do that. If it's no, you go homogeneous. If it's homogeneous, you can treat it homogeneous, or you can treat no, sorry. If not, it's probably linear. And then if it's linear, well, you can do that. If it's a special case, it could be Bernoulli. Or if it's not, it could be exact. All right. And in homogeneous, it can also be exact. Sometimes homogeneous and exactness, sometimes they match. So after exact, this is where you get the inexact form, where you'll start to use this formula. If you remember from my previous video where I used this formula, let me write it down, or the other formula. So this is usually my chart. So first, I'll check if this is separable. Is it separable? You can do this by some algebra stuff. So let's try using the algebra stuff in order to find it here. So x squared y squared plus x y squared, it has this common factor of x y squared, right? And then x plus 2 dx plus x plus 2 dy equals 0. Maybe we can divide both sides by x plus 2 and this that will remove. So we are left with xy squared dx plus dy equals 0. Now we can divide both sides by y squared in order to obtain x dx plus dy over y squared equals 0. Now we can integrate both sides here. Integral of x dx is x squared plus over 2. And then integral of dy over y squared is uh, 1 over y. And that is equal to c, a constant. The integral of 0 is a constant. To make this simpler looking, we can multiply both sides by 2y in order to get x squared y minus 2 equals c. C, since 2 times c is just a constant, we can retain c and then y. Now here, I forgot to write, but there is the condition that, hold on, x equals root 2, y equals 1. You can't see it. Can you? Move that. There you go. There you go. X equals square root of 2, y equals 1. So how do we find c? We would just substitute here this into this. So square root of 2 squared is just 2. Y is just 1. Minus 2 equals c times 1. 2 minus 2 is 0. And c should equal to 0. So x squared y minus 2 equals 0. Or more simply, x squared y equals 2. This could be your answer, or maybe if you want a function of y, we can do that. It's just 2 over x squared. This is also a valid final answer. So this is separable because you can separate the variables and then deal with them one at a time. Question number 2. Is this separable? There's a y prime in here, so it suggests that we move everything y related here to the other side, and and there's nothing in the right hand side, which means we need to put all the x related stuff in there. So let's try doing that. Divide both sides by y squared plus 1. We get 2y over y squared plus 1 times y prime equals 1 over x squared plus 1. We've separated the variables. Separated the variables here. Now we can integrate with respect to the x on both sides. Now, this y prime will tell us that we can integrate with respect to y in this. That's what y prime dx is. If you want to prove that, you can use what they call this integration by substitution in order to do this. So y prime here would be y prime dx would be equal to dv, like that. And then you can say uh 2v over v squared plus 1 dv, but we can skip that and just skip the in to the integral part. How can we solve this? Well, if you remember from the integral stuff, this is an example of an ln, y squared plus 1. And if you check by uh, differentiating it back, you can see that this indeed is the derivative. The other side is an arctan situation. So we will just put arctan x here plus c. And if you're still confused about if this is arctan or whatnot, uh, you can refer to my old videos about integrals. And I will release 100 integrals part 2, so stay tuned, So, uh, the the specific case or what they call this? Basically we have x equals 1, y equals 0. I forgot to put that in. We need to substitute x and y into here. So, ln of 0 squared is 0, 0 plus 1 is 1. Arctan and of x, which is 1. All right. So, arctan of 1 is pi over 4. You can check your calculators for that. Make sure it's turned to radians instead of degrees. Maybe that will mess up with your calculations. ln of 1, again, check your calculators. It's 0, but most of us know that. And then plus c. So, in order to isolate plus c, we need to subtract pi over 4. So, c is negative pi over 4. Going back, our a specific equation is ln of y squared plus 1 equals arctan of x minus pi over 4. And that is an acceptable answer. If you want to, you can multiply both sides by 4 in order to remove the fraction here, but I will leave it at that. Question number 3. 3x squared minus 2y squared quantity y prime equals 2xy. Now, this is probably not exact because 3x squared, 2y squared, it's very hard to remove it from each other. So maybe this is homogeneous since that's the next part of the ladder or the branch. So separable here, and then going down, we get homogeneous. So is this homogeneous? We have to check. So look, x squared, the degree of this one is 2. This one also 2. And this one is also 2. All the terms have a degree 2. Therefore, this is homogeneous. So we can use homogeneous tricks in order to do this. This is usually the hardest one, so I can some literature likes to use y equals xv and vx equals vy, but I like to do this part instead. So divide both sides by what you want. Like maybe 1 over x squared or 1 over y squared in order to make the the degree 0 on both sides. So it's your choice. But in here we have a y prime. That would only happen if we had y equals xv. This is a result of y over x equals v. So we need something that results to y over x. And if we multiply by 1 over x squared, we can achieve exactly that. Watch this. So 3x squared times 1 over x squared becomes 3 minus 2y squared times 1 over x squared becomes 2 times y squared over x squared. This is of the form y over x, but both the numerator and the denominator are squared, so there's that. And then 2xy times 1 over x squared. We cancel one of the x's, we get 2y over x. Okay, now from here we can start substituting y over x equals v. And in order to isolate y prime, we need y. So y equals xv, just like that. So there. Put differentiating both sides, we get y prime equals v plus x v prime. This is the product rule. So now, here we go. 3 minus, I forgot the y prime here. There, that's important. So 3 minus 2 times this is v squared. And then y prime is v plus x v prime. So let's put that equals, on the other side, we get 2v. So we have no choice but to distribute this entire thing. So let's distribute it. Uh, actually, we can do this instead. V times 3 minus 2v squared. Trust me, that will save us a lot more pain later. Plus x times 3 minus 2v squared times v prime. And let's place it on the other side. So 2v. There we go. And then equals 0. Why did I do this? Because there's also v in here and there's v in here. So we can combine them together. So v, 3 minus 2v squared minus 2. 3 minus 2 we can simplify into 1. So this is where 1 minus 2v squared plus x times 3 minus 2v squared times v prime for 0. Now, let's regroup everything with v near v squared. So let's divide both sides by v times 1 minus 2v squared. And at the same time, let's remove this x here. So let's divide by x. So on one hand, 1 over x. On the other hand, 3 minus 2v squared over v times 1 minus 2v squared. V prime equals 0. Now it is now separated. So it's now separable DE. So we can integrate both sides with respect to x. And the v prime gives us a green light that we can integrate this with respect to v. Now, this is easy. This is not easy because we need to do partial fractions. So, very exciting, I know. So this is how we're going to do it. V and 1 minus 2v squared. Or, yeah. Actually, let's rearrange things together so it's easier. Oops, sorry. This is really bugging me. Like 1 minus 2v squared. Can it be 2v squared minus 1? Yes, if we move it to the other side. So it would become negative, and then this would repel the negative and would turn positive. So integral 1 over x dx equals integral of 3 minus 2v squared. Let's not do the top one. I just want the bottom one fixed. Over v times 2v squared minus 1 v prime dx. There you go. Again, v prime dx means we can integrate with respect to v. So a over v, bv plus c over 2v squared minus 1. Since this is 2v squared, we can put 4 in here because 4v is the derivative of 2v squared. 2v squared. So we can put 4v squared here. The c is just there for completeness. Okay, so let's do this. Cross multiply. We can do that. So this becomes 2av squared minus a plus 4bv squared plus cv. This is over v times 2v squared minus 1. This is supposed to be 3 minus 2v squared. Ah, what do you know? So, this top one right here should match. So, let's compile everything with a v squared, a v, and the constant. So, v squared, 2a plus 4b should be negative 2. Oh, negative 2. And c, well, it's not there, so it should be 0. Then negative a is 3. A is already negative 3. That leaves b in here. What is it? So negative 6 plus 4b equals negative 2. Put that on the other side. We get 4b equals 4. B is equal to 1. So c is 0, a equals negative 3, and b is 1. So let's reconstruct the integral. Negative 3 over v dv, or that's just v prime dx, whatever. Same thing, plus 4v over 2v integral, sorry, 2v squared minus 1 dv, and c is nothing, so we can ignore it. And let's put integral of 1 over x dx right there as well. So equals integral 1 over x dx. Okay, so let's integrate both sides. Integral of 1 over x, easy, ln x. Let's put plus c in here because there's a lot going on the other sides. So do that. And then negative 3 ln v, that is going to be the answer here. And this is obvious. We can just take negative 3 on the other outside, then 1 over v dv, that's ln v. Plus, this should be ln of the inside, 2v squared minus 1. And if you do integration by substitution, by doing 2v squared minus 1 equals u, and then derivative is 4v dv equals d mu. So it's going to be ln, no problem there. So in order to solve this, we need to compile everything with an ln on one side. We're lucky that this has all ln on all of its terms, because if it has arctan, we can't do this trick. So c equals negative 3 ln v minus ln x plus ln of 2v squared minus 1. This is where it gets very satisfying. We can combine everything into one big natural logarithm. The positives on top, 2v squared minus 1. The negatives on the bottom, x, and then this should be v cubed. We can raise the power inside with the multiple of the natural logarithm according to the laws of logarithms. And since it's negative, we can put it on the bottom. Satisfying. Because now we can raise e to both sides to remove that pesky natural logarithm. And e to the c is still a constant, so that's going to be still a constant. We can name it another constant, but I like it just c, you know, unchanging. So 2v squared minus 1 over. This is xv cubed. So I like to do it like this. Xv times v squared. Why do you think that? Hmm. Hmm. Xv is y. So we can put y in replacement of that xv and put everything else on the shelf. And the bottom of the shelf as well. All right. So now we can multiply both the numerator and the denominator by x squared. We get 2y squared minus x squared over y cubed is there, and x squared is gone because it cancels out, and that's the answer. If you want to be complete, you can multiply both sides by y cubed. So 2y squared minus x squared equals cy cubed. And there you go. I believe that's the answer. There is no specific condition. So there you go. This is a single line solution, which is usually prettier looking. So we're going to be using that. Number four, y squared dx plus x squared plus 3xy plus 4y squared dy equals 0. Is this separable? No. Is this homogeneous? It looks homogeneous. So let's give it a try. What do we start from? You can certainly divide both sides y y prime uh by y squareds in order to get we can certainly divide both sides by x squared like we did last time. But we can also divide by y squared if we're so inclined. And how would that benefit us? There's this dx here. It's alone. If we divide both sides by y squared, this would be more alone. I would like that. So promote dx to x prime and promote dy to nothing, just one. This is basing the derivative, the dy and the dx with respect to x fully. With respect to y, sorry. Because dy over dy is equal to 1 and dy over dx is x prime. So that's going to be what we're doing. Some would say that this is dividing by dy. I don't say that because dx and dy are not quotients. They're not numbers to be divided and multiplied upon. But you can believe that if you're only working with first order differential equations or if you're an engineer. But let's do this. Let's divide both sides by y squared. What would that entail? X prime plus. This would be x squared over y squared. This would be 3x over y. This would be 4. And dy would be 1. So there we go. 0. Hmm. We could go for a Bernoulli here, but that's not meant until later. We already have a situation in here. It's called a homogeneous, and I don't think Bernoulli would work either. So let's put homogeneous on the table. So x over y is v. X is vy, and x prime is v plus, uh, let me remember that. Yeah, v prime y. Okay. So, or y v prime, whatever you want. And there you go. So on the one side, we get, sorry, x prime should be v plus vy prime y. Or let's just put yv prime. Why not? Plus v squared plus 3v plus 4 equals 0. Hmm. We could add v to this v. We get yv prime plus v squared plus 4v plus 4. Do you smell that? Because I smell a perfect square. Let's see how it goes. This is now separable, so we can divide both sides by v squared plus 4v plus 4, and we can divide both sides by y as well. And v squared plus 4b plus 4 is a perfect square, so it's v plus 2 quantity squared. That's nice. And then y. This is now separated. We can integrate both sides. 1 over y, sorry. We can integrate both sides with respect to y. Again, v prime says this is a batch, meaning we can integrate with respect to v. So, uh, dv over v plus 2 quantity squared, same thing. So, what is the derivative of that? Recall that the integral, sorry, of dv over v squared, that would be negative 1 over v, since the derivative of that is 1 over v squared. So, and because this is v plus 2, there is no what do you call it? Chain rule shenanigans, I guess. So we can say this is negative 1 over v plus 2. You can check it if you want. Plus ln y here. And don't forget, we're also integrating the other side. So this will be c. Nice. So now we can substitute v back into x plus y. So negative 1 over x over y, I mean, not x plus y, x over y plus 2 plus ln y equals c. There we go. And we multiply both the numerator and denominator here by y, we get negative y over x plus 2y. Ah, yeah, this is just 2. Sorry. Uh, 2y. Sorry for the error. Plus ln of y equals c. If we want to make it look proper, we can multiply both sides by x plus 2y. This is called a single line solution. Makes things cleaner. And that is going to be your answer. Oh, sorry. Forgot about this. And that's going to be your answer. Negative y plus quantity x plus 2y times ln y equals c times x plus y. So that's cool. Question number 5. Y squared dy plus x times x dy minus y dx. Hmm. Oh, there's a problem with the problem. I'm missing something. E to the x over y. Now, this is interesting. Basically, there's an x over y in here. You know what that means? It forces us to do x over y equals v. So now we can divide both sides by y squared. So dy plus this is going to be x squared over y squared dy minus this is y over x dx. So, uh, and we can forget about e to the x over y right here. I think I messed up the problem. Hold on. Let me erase this. Okay. I think I messed up the problem. Sorry. I'll cut that out. Y squared dy equals, sorry, x times x dy minus y dx e to the x over y dy. The solution is we multiply both sides by y squared because of the xy. It's a bit different from what I said earlier, so pardon my forgetfulness. X squared over y squared dy minus y over x dx to the power e to the x of y. Whew. So since we are only focused on x over y, that should be our focus, x over y. And x equals yv. X prime equals v plus yv prime. So instead of this dingy dy and dx, let's put a shiny x prime on dx and 1 on y's. So this dy becomes 1. X squared over y squared equals v squared. And let's put e to the v here, just in case. And minus y over x. This is x over y. Sorry, I'm a bit stupid now. And this is v and dx is x prime, so that's going to be let's just put e to the v then x prime. X prime has changed into that, so let's put that there. There you go. So let's spread the love. by distributing this. So v squared e to the v minus v squared e to the v plus y e to the v, y v e to the v, v prime. This, that, cancel. That leaves us with 1 equals y v e to the v prime. This is great because we can now divide by y. So 1 over y equals v e to the v prime. It was now separable. Now we can integrate with respect to y. This becomes ln y. This becomes, let me see. Oh, we need to use integration by parts. I recommend using the DI method for this one. So DI and then plus minus plus, you can set up that. So D, we can put V in there and then e to the V on the integral side. So in here we get V, integral of the derivative of that is 1, derivative of that is 0, and we stop. Because it's a 0, we will stop there. E to the V continues like that. And then we can multiply the diagonals and then we can stop at 0. So V e to the V minus e to the V plus C is the right hand side. So now let's rearrange a little bit. So, for example, this can be v minus 1 quantity e to the v. Let's see. So ln y remains ln y. V goes x over y minus 1. Then e to the x over y plus c. Now, in order to make this look cleaner, we can multiply both sides by y. We get uh, negative. What's a negative? Oh, I forgot to. Oh, sorry. I forgot to make this negative. Sorry. In the process of making this negative, let's make this positive. Let's make this negative. So negative ln y on one side. So multiplying both sides by y gives us negative y ln y equals x minus y and then e to the x over y plus cy. And it's the answer. All right. Now, after homogeneous, we can go on to the much prettier part of differential equations, which is linear. So is this linear? Let's arrange it into something that looks linear. So y prime, and then this has a y term in it, this thing. So we need to move it to the left hand side. Minus 2xy, and this doesn't, so this is e to the x squared. Remember that the form that we are targeting is y prime plus p of x, y equals q of x. So does this satisfy this? Yes. So now we can use the integrating factor mu, which is going to be e to the integral of p of x, which is going to be negative 2x dx. This is going to be negative x squared. Plus C, do we need? No, we don't need plus C. Let's say C is 0 for simplicity's sake. Maybe there is another world where C needs to be something else, but we can choose 0. It's fine. No one cares anyway, so we multiply both sides by e to the negative x squared minus 2x e to the negative x squared y equals e to the negative e to the x squared times e to the negative x squared. That's just going to be 1. There you go. Due to the loss of exponents. Looky here. Huh. Is it just the derivative of y e to the negative x squared? The derivative of e to the negative x squared is this, right? It's e to the negative x squared times the derivative of the inner function, which is negative x squared, negative 2x. That is exactly the point of this special integrating factor mu, to do this. So that's going to be interesting. One on the other side. Integrate both sides. Now we are face to face with two of the hardest integrals you will ever come. The integral of a derivative, which is just the function. Oh my god, this is difficult. Look at all you had to do is this. So difficult. Mhm. And the integral of 1. Oh my God, that is even more difficult. Oh, please. This is going to be x plus c. Forgot about plus c. Now, the I don't want negative in here, so let's multiply both sides by e to the x squared. We get y equals, let's make that, e to the x squared plus c e to the x squared. Now, I didn't write this, but there is a specific condition. Mm, number 6 here is x equals 0, y equals negative. Okay, so what you do is, again, to just put everything in this equation. Y is negative 1, so negative 1 it is here. X is 0, so 0 here, e to the 0 here, plus c times e to the 0. All right. C times e to the 0, that's going to be c, and 0 times whatever is just 0. And then this is negative 1. C is negative 1. So y equals, this have e to the, these have e to the x squared. So we can put that outside, factorize it, then x minus 1 here. And I believe that's going to be our final answer. That is the specific solution. All right, next question. Ooh, interesting. And now let me check if there is. Yes, this passes through the origin. All right. I think we can see what that means later, but let's pay attention to here. This looks like it is linear, right? Again, if you're not sure, I know this is linear, but if you're not sure, you can always run through your conditions. Is it homogeneous? Is it separable first? Actually, yes, this is separable. Would that help you? Maybe, but let's say this is linear, you know? We can solve it later with separability, but let's see here. There's the one in here, probably not separable in the moment. Sorry to burst your bubble. It's probably not separable, but it's still linear. Let's divide both sides by x in order to isolate y prime. I don't want that y prime tainted by x. So y equals, y prime plus, divide this by x. Let's distribute the division. You will see what I mean. So 1 over x plus tangent x. Since x divided by x is just 1, y equals 1 over x on the other side. Now, look at this. This is the p of x. So mu of x is e to the 1 over x plus tangent x. Oh, sorry, minus tangent x. I would have been impossible with plus. Minus tangent x. Sorry. And this is the ln x minus ln of secant x. But, if it's negative on the outside, it means secant x to the negative 1, right? Or 1 over secant x. And what is 1 over secant x? That is cosine x. So e to the ln x times e to the ln cosine x. This is positive, and then we separated using the law of exponents. E to the ln x is x. E to the ln cosine x is cosine x. And that's going to be our special integrating factor, mu. So, let's put it back into the differential equation. So, x cosine x y prime plus, and then in here, x cosine x times 1 over x, that's cosine x. X cosine x minus times tangent x. Well, we multiply it by tangent x, which is just sine over cosine. Cosine cancels out, we get x sine x dx. Y equals 1 over x times x cosine x is cosine x. And look what we have here. This is indeed the derivative of this, which still proves that the formula works. So let's put d over dx, and then xy cosine x equals cosine x. Integrate both sides with respect to x. This is going to be another difficult integral. Integral of a derivative is canceling each other out. So xy cosine x. And then cosine x derivative, that's just sine x. Let's see. And you can stop there, but we still have the condition that it passes through the origin. So the origin is 0, 0. So x and y need to be 0. So x times y, xy 0 times 0 times cosine 0, whatever that is. Yeah, I don't care. Equals sine of x, sine of 0, plus c. Don't forget plus c. That just means c equals 0, which is good. So yeah, xy cosine x equals sine x. There you go. That could be your answer. Or if you want a function of y, a function of x, y equals 1 over x tangent x, or y equals tangent x over x. Wonder if they'll make an integral of that. All right, question number 8. Question number 8. Where is question 8 in this house? Ah, there it is. Here you go. Secant y dy over dx minus 1 over x cosine y tangent y equals cosine y sine y tangent y. This awfully seems like a mishmash of whatever, whatever, whatever. Huh. What do we do? If we multiply by secant y on both sides, what would happen? Usually, those kind of questions are the first step to solving this kind of stuff. So let's see. Secant squared y on this one and dy over dx minus cosine y, secant y, they cancel each other out. So we are left with 1 over x tangent y. If we multiply secant y with sine y, that gets us tangent squared y. Hmm. Do you see it? It's linear and tangent y. And I will teach you another method in doing that. You can use the method that I did in the videos linear and fy, but this is another method. Tangent y equals v. Secant squared y dy over dx equals dv over dx. This is differential equation by substitution. Who would have thought, right? So secant squared y dy over dx equals dv over dx. So we get dv over dx in here minus 1 over x here. Tangent y is v and tangent y is v squared. Cosine x is there. What do we see? Bernoulli. This is Bernoulli. And that's amazing because I didn't thought that was possible. But Bernoulli's here now. Bernoulli's here to stay. We need to divide both sides by v to the v squared. Sorry. So v to the negative 2 dv over dx minus 1 over x v to the negative 1 cosine x. Now this is a Bernoulli case, so we can say v to the negative 1 equals what another letter we can use? Alpha. We've run out of letters at this point. So v to the negative 2 uh v dv over dx equals, let's just put alpha prime here because that's easier to write. So this is alpha prime minus 1 over x alpha. Oh, sorry, I forgot the negative here. So this should be negative a prime. I'm kicking myself right now. Let me see. Yes, all right, that's correct. Equals cosine x. Cosine x is pretty much unaffected in this situation. And since there's negative, we have to multiply both sides by negative. So alpha prime minus, plus, sorry, 1 over x alpha equals negative cosine x. Now, how do we do this? We we invoke the special integrating factor mu. It's still relating to x, so 1 over x dx. This is e to the ln x. Standard fanfare, this is x. Multiply x on both sides. X alpha prime equals plus alpha equals negative x cosine x. On one hand, it's pretty much done, one and done here. X alpha d over dx, whatever. On the other side, we have a integration by parts to consider. So negative x in here, cosine in here. Uh, Negative x derivative negative 1 derivative 0. Cosine x integral sine x integral negative cosine x. This, that, they are multiplied together. Uh, so on, we'll see about that. Actually, negative x cosine x. Integrate both sides. Luckily, we already have the integral in here. So x alpha equals negative x sine x. Minus minus minus, that is a negative cosine x. Let's see. Alpha is v prime back there. So x v prime negative 1, v to the negative 1 equals negative x sine x minus cosine x plus c. Sorry. Yeah. Okay. And v to the negative 1. That what v is tangent y. So v to the negative 1 is cotangent y, which is cosine y over sine y. I'm going with that in here. So x times cosine y over sine y equals negative x sine x minus cosine x plus c. Multiply both sides by sine y, we get x cosine y equals negative x sine y minus cosine x, let's put x first. Cosine x sine y plus c sine y, and that's your answer. And yeah, all right. We've done the linear. We've even done a Bernoulli. All right. Number nine. All right. Number nine. 2xy minus tangent y dx plus x squared minus x secant squared y dy equals 0. Is this separable? No, because there's y inside functions and there's y outside the functions. That's a pretty good sign of not being separable. Is it homogeneous? No, because the degree is not exactly equal to each other. This is degree 2, this is degree 2, but this only has degree 1, and this doesn't even have a degree. So yeah, no, not for homogeneous. Is this linear? I don't see if it's linear. Is it even Bernoulli? I don't think so. So let's go to exact. Let's check for exactness. This is M, this is N in this scenario. So M, and this is dx, partial with respect to y. So 2xy, derivative of the with respect to y, that is going to be 2x, minus derivative of tangent y with respect to y is secant squared y. Keep that in mind. Nx. All right. So uh, derivative of x squared with respect to x, that's 2x. Derivative of this with respect to x, well, this is with respect to y, so that's just a constant. So x is really the player here. So derivative of x is 1, so secant squared y. And would you look at that? They're exact. So we can start with something that's less threatening. M or N, pick your poison. I'm going with N. And I know N is a partial derivative of f with respect to y. So this is x squared minus x secant squared y. Let's integrate both sides with respect to y. All right, here, what is the what is the integral of x squared with respect to what? It's not x cubed over 3, that's not it. This is x squared y. Since x squared in the y world is just a constant, that's a helpful tip. Consider this belongs in x, then secant squared y, tangent y. Since this is just y and we still have the world of x to go, we have to add g of x here. All right. Now, partial this with respect to x. X squared y, the derivative of that with respect to x is 2xy minus x tangent y just becomes tangent y plus g prime of x. Look at n, m. It was 2xy minus tangent y. Clearly, this matches, so this should match. What matches? 0. G prime of x equals 0. G prime, or G, sorry, is the integral of 0, which is constant. So there's nothing interesting in here. Let's assemble. So we get x squared y minus x tangent y, and g of x, there's nothing, it's just c. So we're going to put the c on the other side. And that's going to be your general answer. All right, on to the final question. Let's look at this. Ooh, there's fractions. It's bound to be difficult. Let's go to the list. Is it separable? It doesn't look like it. All right. If it doesn't look like it, it's probably not separable, but you can try. Maybe you will fail, but at least you try. There are some people that just won't try, and that sucks. Is it homogeneous? Not a chance. That's one. Is it linear Bernoulli? I don't think so. What's next? Is it exact? That's the final resort that we should be looking. If if your teacher just handed you a question and then you had to ask solve this first degree ordinary differential equation, go through that list, and at the end check if it's exact, because usually it's probably exact. If it's not exact and none of the others fit, maybe you did something wrong, or you should probably pray, or probably don't take that question, because probably haven't learned it. So this my, what is its integral with respect to y? That's good. That's kind of difficult. This 3x squared term, well, in the y world, if we're partial differentiating it with respect to y, it's 0, so we can ignore that. What we can't ignore is this big fraction. We can use quotient rule in this one. All right, so quotient rule. Derivative of the top times bottom. So 1 plus x squared y squared minus top times derivative of bottom, which is 2x squared y, equals, this is 1, yeah, 1 plus x squared y squared minus y, or 2x squared y squared over 1 plus x squared y squared quantity squared, or 1 minus x squared y squared over 1 plus x squared y squared quantity squared. All right, NX, let's check for that. Some people would give up on this because it sounds convoluted, but maybe it's worth a shot. So on the other one, this is x over 1 plus x squared y squared. Again, quotient rule, so 1 plus x squared y squared times the derivative of the top, which is just 1, minus top times derivative of bottom. So derivative of bottom with respect to x is 2xy squared over 1 plus x squared y squared squared. So this becomes 1 plus x squared y squared minus 2x squared y squared on the top over 1 plus x squared y squared squared. So 1 minus x squared y squared over 1 plus x squared y squared. I remember x squared. Okay. These are exact. We have proven it's exact, therefore we can proceed with the solution. So look, let's start with the less intimidating one, which is this one. So n, which we know is fy, or partial of f with respect to y, x over 1 plus x y quantity squared. X squared y squared is just that, so we can use that. So now let's integrate both sides with respect to y. So integral of x over 1 plus xy quantity squared times dy. What is that? Well, isn't this arctan of xy? If you don't believe me, integrate the differentiate this, we get 1 over 1 plus x squared y squared. Then multiply that by the derivative of this, which is going to be x. So this matches. And since this is not the end, since we still have g of x. All right. F of x, sorry. Partial f with respect to x is going to be in here. It's 1 plus x squared y squared. And on the top, the derivative of this with respect to x. So this is going to be y. Then g prime of x. N is, this is n? I said f. M. M is y over 1 plus x squared y squared. And if I check my notes, plus 3x squared. So g prime is equal to 3x squared. That means g is x cubed plus c. All right. So we can now assemble everything we need. So y over 1 plus x squared y squared plus x cubed. And we can put c on the other side. That is oh, sorry, I forgot. Not this one. Arctan. Why did I write that? Arctan of xy plus x cubed equals c. That is the true final answer. But is that the final question? I don't think so. Because we have question 11. Surprise. Right. Xy prime plus y equals y squared x squared ln x. This looks Bernoulli. I mean, there's y prime here, there's y here, and there is y squared here. This looks like a Bernoulli situation. So maybe it is. Let's divide both sides by x. So y prime plus 1 over x, y equals y squared times dividing by this by x becomes x and then x. This is definitely a Bernoulli situation. So what we do in that situation, we multiply both sides by y to the negative 2 in order to cancel this y to the negative 2 on the other side. Then 1 over x times y to the negative 1 equals x over x. Y to the negative 1 should be v. Negative y to the negative 2 by prime is v prime. That's nice. So this becomes negative v prime plus 1 over x times v. And this is x and x just like that. And v prime minus 1 over x, v equals x and x. All right. E to the negative 1 over x dx. E to the negative ln x. Or e to the ln of 1 over x. Or x, 1 over x. So 1 over x is our special integrating factor. 1 over x minus 1 over x squared v, v prime here, equals 1 over x times x is 1. So ln x just on the other side. Integrate both sides. This is just a simple d over dx, v over x integral. And the integral of ln x can be done by integration by parts. Let's put the I here. And ln x can be put here. And what do we put on the I? We put 1. So ln x derivative is 1 over x. I derivative is x. So not crisscross, just that. And then we have to integrate this together. So x ln x here minus the integral of 1 over x times x, or just 1 dx minus x plus c. On the other hand, we have the derivative, the integral of a derivative. So that's v over x. We can multiply both sides by x. Oh, no, no, sorry. Hold on. Uh, v is y to the negative 1. So we can put 1 over xy equals x minus 1. Oh, wait, sorry. X times ln x minus 1 plus c. I can do that. Then we multiply both sides by xy if we want a nice answer. So we get 1 equals x squared y, then ln x minus 1 plus c xy. That's going to be the answer. And yeah, that's it. So that is the answer for number 11. That is the 10 differential equations. It's short and I haven't included everything, but I hope that helps you in your exams. So I'll see you in the next video where I answer 100 integrals. Maybe, but it will come soon. See you later, Sanderheads.